We found the displacement as a function of time and showed it sinusoidal. Now we're going to move up to velocity, of course, and then after this we'll do acceleration. So velocity is dx dt, so we take the derivative, which we've already done when we set this as our guess, and we find that the velocity is minus a omega sine omega t plus phi. So the amplitude of the velocity versus time function is not a like it was for displacement, it's omega a. As promised, we will now move to acceleration as a function of time. In this case, we take the first derivative of the velocity. Again, we did this earlier when we were solving Hooke's law equation, the differential equation. So we have d by dt of minus a omega sine omega t plus phi. And we get the acceleration at any point in time is minus a omega squared cosine omega t plus phi. In this case, the amplitude of the acceleration versus time function is omega squared a, not omega and not a. Notice what is not changing on all of these graphs. Right here, omega, the angular frequency. Let's look at all three graphs together now. And the first thing you notice is that each one of them has the same exact period. If you go peak to peak on each one of these graphs, you'll see that the period is the same. So let's look when the position is at a positive amplitude. So where can we go? Well, might as well start right up here, right at the beginning. So you have a positive amplitude for position. What's the acceleration? Acceleration is negative, max. And let's look at the velocity, it's 0. When your position is at your negative amplitude, here, just draw the line down here, you find that your acceleration is positive, okay, over here, and your velocity is zero, your velocity is 0. Now this should all square with the stuff we did when we first started this unit. So the velocity is at a maximum when both the position and the acceleration are 0. And we found that out. That's when you're at the equilibrium point. The spring is passing through its relaxed point, if you will. And again, I like to harp on this, relating simple harmonic motion to sinusoidal motion, so please click on the video. Here are the graphs of kinetic energy and potential energy versus time for an object in simple harmonic motion. Again, we did this earlier in this unit. And let's see, let me just sketch it down here what we had then. Hopefully this will ring a bell. Had a curve like that, and a curve like this. This was our total energy. Okay, and which one of those would be the potential energy? That would be this curve right here, right? Because it's a maximum at the endpoints, and kinetic energy is a maximum in the middle. So what do you notice when you look at these two graphs of kinetic energy and potential energy? When one graph is at a maximum, the other is equal to 0. And the sum of the energies at any point on the two graphs is a constant, 9.5 on the y-axis. Right, you see that up here. See, it goes right over to 9.5. We call these out of phase by theta is equal to pi. Phi is equal to pi. That's the phase angle. Now we will put all three motion variables on one graph. And we're going to plot them with different units and scales on the vertical axis. And you can do that. You can add, these numbers are somewhat arbitrary over here. Don't worry about them. But you could have one scale for acceleration, one for velocity, one for displacement. And you would put those numbers over here. Now we know they have to be different, right? Because the max for the displacement, the maximum value would be a. The velocity would be omega a. And the acceleration maximum value is omega squared times a. But this is a nice graph to show their time behavior and their relative magnitudes. And now we're going to set you up for some problems that are going to end this unit by showing you the periods of the motion. And then we'll ask you various questions about the behavior of the displacement, velocity, and acceleration. Then you'll be done with this unit. So we're going to say, here is one period, and we're basing that off of, let's see, it looks like we did it off the displacement, right? Because we started here. We came down, up, came back to where we started from, and started repeating our motion, right? Because it's going to go down after that. So this here is a period, and then we just went ahead and marked half a period, 3/4 of a period, and 1/4 of a period. And you'll be using this on the last few slides of the unit.